So the mathematical definition is represented by the integration. This is the mathematical represented. What does it mean? So we need to find the integral of the function x respect to the independent variable x evaluated between limits from a to b. So it's the integral of the function x respected to independent variable x evaluated between the limits of x is equal to a and x is equal to b. So in a graphic way, or what you want to do in here, if this is my limits from a to b, and this curve here is represent my function, I need to calculate the area between a and b under the curve. So for the non-computer methods, for differentiation and integration, both of them is the same. So the function to be differentiated or to be integrated will be typically one of these three forms. So the question is coming out from this chapter is going to be one of these forms. Maybe you are going to have a simple continuous function, such as a polynomial or exponential. Or maybe you are going to have a complicated continuous function. It's going to be difficult or impossible to integrate directly. Okay. Or you are going to have a tabulated function where the values of x and the function of x will be given. So we are not going to have the first one. We are not going to have anything from the second one. This is what we are going to have. A tabulated function where the value of x and the function of x is going to be given at a number of discrete points. So and somehow this is like to simulate what happened in the experimental fields of data. Okay, so we're going to have a table here. And somehow it's going to be something like this. We are going to have the values of x and also the values of the function. So since this one is talking about the differentiation, this is we are going to cover it on the next, on the coming lab. Okay, so what we are going to get, or what we are going to have for our class today, we are going to have a table of discrete of values of x and generated for the function. So this is what we are going to get, x and the values of the function, and we are going to try to calculate what's the area under the curve between the limits of a and b. So how we are going to do this? We are going to use some numerical methods to estimate the integral of the basis of the discrete point. So this is what we are going to focus about, how we are going to use the numerical methods to estimate this area under the curve using methods. We are going to call it's the Newton codes. So the Newton codes, this is what we are going to cover today. Newton codes integration formula. This is the most common numerical integration schemes. The idea here, it's based on the strategy, is we are replacing the complicated function or a tabulated data with an approximating function that is going to be easy to integrate. And we are saying here it's approximating. So when we are approximating here, that means there will be two types of error you need to calculate. Maybe you're going to calculate the relative error if you have the true value, or most of the time you are going to calculate the approximate error because most of the time maybe you are not going to have the true value. Okay, so this is the types of the segments that we are going to face, and what we are going to use based on the Newton codes, because Newton code is we can calculate based on traps and Simpson rule. So this is what we are going to take first. We are going to talk about traps. So if you are talking about the traps, is the first order polynomial is going to give you a straight line. So this is the straight line. So we need to calculate this dashed area here. If you are talking about the Simpson rule, so we are talking about the parabola, which is going to be employed to approximate the function. But you can see from here, it's more accurate than traps, as we are going to see from the example and the exercise that we are going to do. Okay, so No worries about this part. We are here also. We are not interested to learn about the open forms of the Newton codes. We will just only focus on closed. So this means the limits a and b, it's going to be provided. We are not talking about this part. We just only focus on this. Closed forms where the data points are beginning and the end, the limits of integration are known. So this means you know the value of a and the value of b. So the first method for today, or the first rule, is the trapezoidal rule. So the trapezoidal rule is the first Newton codes closed integration formula, and it's correspond to where the polynomial is the first order. So this is the case that we are talking here about. It's the first order polynomial. It's going to be giving you a straight line under the curve. This is the first order polynomial. This is for the trapezoidal rule. So the area under the first order polynomial is an estimate of the integral of the function between the limits of a and b. So how to calculate the area under the curve for a trapezoid or the first order polynomial? This is the function that you're going to use for the trapezoid rule. So the integral will be equal to b minus a, your limits, times the function of a plus the function of b over 2. From where actually this rule, or from where this equation is came, graphically, this is how it looks like. Geometrically, it's the trapezoid rule is equivalent to the approximating area of a trapezoid under the straight line. So we know it's to calculate the area of this trapezoid, it's equal to the height. The area of trapezoid is equal to the height times the average of the base. So this is the height, and you need to get the average of the base. Okay. So now, in our case in here, if you take this trapezoid and you rotate it about like 90 degrees, so this is going to be your width, which is considered your base, and this is going to be your height. So that's mean the integral for this shape of trapezoid will be equal to the width with the average of height, because we transpose it into 90 degree. Okay, so in this case in here, what's actually it's the width and what's the average of the height. Okay, your width here is supposed to be a and b, your limits. In our case in here, this is your width from a to b. This is the width times the average of the height. How you are going to get the average of the height? To get the average of the height, you need to get the function of a plus the function of b, and you divide over 2. So this is the average of the height. So now if you combine all, this is your width, and this is the average of the height. So this is how the trapezoid rule is came up. Okay, this is from the graphic here. So no worries about the equations. You don't need, as I said before, you need for you to remember them. We are going to provide you in the appendix all the equations that you need to solve for the exam. Okay, so now since we are saying here from the beginning, it's what we are trying to do here. We are trying to approximate. So that means we need to calculate the errors. If you have the true value, so you can calculate the relative error. If you don't have the true value, so you need to calculate the approximate error. So to calculate the approximate error for the Newton codes, it's slightly different from what we had learned before, because there is an equations to calculate the errors. So to calculate the error of the trapezoid rule, so when we are going to employ the integral under the straight line, the error is going to be substantial. The error is going to be huge. As you can see from here, let's back to this figure in here. If this is trapezoid and we are trying to cover the area under the curve, we calculate this dashed line. How about this area here? We didn't take it into account. So we didn't calculate, we didn't touch this area here. So that means the error really is going to be very big. Okay, why? Because this is a straight line under the curve. So how to calculate this error? Because we need to quantify it. By the way, this is not ET, this is EA. This is the equations how to calculate the error of Trapezoidal rule. It's equal to negative 1 over 12, and you need to find the second derivative of the function. The z sign here, that means you need to find the mean of the second derivative of the function. I'm going to tell you how to find this. Times b minus a cubed. Or what we can tell it is about negative 1 over 12. And this dashed line here, that's mean you need to find the mean of the second derivative of the function times the limit cubes. Okay, so while we are going to do the example, I'm going to tell you how to find the mean of the second derivative of the function. So let's start with our first example, and after that we are going to go for the multiple application of trapezoidal. So this is our first example here. I think the page number is not correct because this is referred to the old page. So let's see the example. I'm having this function in here, and if I'm going to use those values of from 0 to 0.8 inside this function, is going to be generate for me all these values. Okay, so I have this function, and I need to use the Newton codes to calculate the integration or the integral for the area under the curve. So if I put 0 here for this function, so the constant is going to be equal to 0.2. If I put 0.1 inside this function, the answer is 1.289 and so on. So nothing here. So this is your table now. Okay. So now I need to find the integral for the first order polynomial here. So this means it's a straight line. So the equation is equal to what? The integral will be equal to b minus a, your limit, which is your limit here from 0 to 0.8. So it's going to be equal to 0.8 minus 0 times the function of a. The function when x is equal to 0, it's 0.2. So it's 0.2 plus the function of b, which is 0.8 over 2. So that means you are not going to do anything from all these values here. Okay, so this is a, this is b, from 0 to 0.8. So it's 0.8 minus 0 times the function of a, which is 0.2, plus the function of b, which is 0.232 over 2. The answer is going to be 0.1728. Could you please try this one? I will give you about like 2 minutes. You need to go with me one by one. If you have any questions, you can stop me and ask me. Managed to get the answer? This value? Okay, so now it's really easy. As I told you, you are going to have a table. That table, it has the values. So you just only apply the equation. So it's b minus a, 0.8 minus 0 times the function of a, which is 0.2, plus the function of b, 0.232 over 2. It's supposed to get the integral will be equal to 0.1728. Okay, so now you get the value, but now you need to check the error. If I have the true value, I can calculate the error. If I don't have it, so I need to calculate the approximate error. So now let's say that I have the true value, which is 1.64 here. So to calculate the true value or the error is going to be equal to true value minus the results. So it's 1.64 minus 0.17. This is the true value minus the results I got. So the answer is 1.46. If I want to get this value into percentage, so I need to divide again over the true value. So this is the value of the approximate error in percentage. It's 89% error. It's huge. But actually, it's most of the time, you're not going to have this true value. It's not going to be available. So you need to calculate the approximate error. So to calculate the approximate error for the traps, this is the equation that you need to choose. Negative 1 over 12, and the mean of the second derivative of the function. So actually, it's like the parts that it's missing here, it's the mean of the second derivative of the function. Okay. So how actually to get the mean of the second derivative of the function? We are using this equation to find the mean of a function. In general, to find the mean of any function, you need to integrate the function and you need to divide over the limits from b to minus a. In our case in here, you are not going to integrate the original function. It needs you to integrate the second derivative of the function. So what we need to do in here, you need to differentiate this equation or this function 2 times. Then you put it back inside here. So with the piece of paper, could you please differentiate 2 times? If you didn't do that, you're not going to understand and you will feel confused. So differentiate this function here 2 times and follow what I'm going to show you from the textbook. Supposed to be when you are going to differentiate this one is 2 times, this is what you are going to get. Here in the textbook, they are saying it's in actual situations, we are not going to get the knowledge of the true value. So therefore, we need to calculate the approximate error estimates is going to be required. So to obtain the estimates, the function's second derivative over the interval can be computed. So this is the second derivative of the function, of this function here. So you need to differentiate 2 times to get this. Okay, so you are now having the second derivative of this function. You can see from here that the requirement is we need to make -1/12 with the mean of the second derivative. So this is the equation here. How to find the mean? I need to find the mean of the second derivative of the function. So I need to integrate it and make it b minus a. So in our case in here, this is the second derivative. This is the second derivative. And this is how to find the mean. So I'm going to integrate the second derivative function from 0 to 0.8 from my limit over the limit from 0.8 minus 0. So the answer supposed to be coming is -60. Could you please try to do this calculation? Integrate this second function here to get the answer here of -60 using the equation of the mean. We get the answer of -60, right? Okay, so now when you get the answer of the mean of the second derivative is equal to negative 60. So now you can use these equations in here to compile all the numbers. So the approximate error will be equal to negative 1 over 12 times negative 60 times p minus a 0.8 minus 0 q. So you get the answer of 2.56. So somehow this is the one you are going to get. Okay, negative 1 over 12 times the mean of the second derivative of the function, which is negative 60. This came from here with the limits from 0.8 minus 0 cube. So the answer is 2.56. So now you already managed to calculate the approximate error of one single edge of traps. Okay, so the next thing in here, still we are talking about the trapezoidal rule. The previous example, what we have done, we are using the traps rule just only for one segment, which is from the segment that we use. It's from 0 to 0.8, and we didn't divide the area between A and B to any other segments. So that's why here it's the error, it's really high. So if we are going to use a multiple application, multiple segments of traps rule, this is going to be improve the accuracy of the traps rule, and is going to be reducing the error. So one way to improve the accuracy of traps rule is to divide the integration interval from A to B into a number of segments. And we are going to apply the same techniques to calculate for each segment. So the area of individual segments can be added to yield an integral of the entire intervals. Graphically, what you can see, if this is my curve here, and instead of I'm going to use one traps rule, which is the error is going to be very high. If I use two segments of traps rule, so that's means from A to B, and this is again from A to B. But now we are using x0 to x1 and from x1 to x2. So this is two segments. This is segment number 1. This is segment number 2. If we are going to calculate the area of the error here, the error is going to be more lesser than the one segment. If you add more segments, so that means from x0 to x1, this is your first segment. From x1 to x2, this is the second segment. From x2 to x3, this is your third segment. You can see the errors start to be reduced. The more you add segments, the more you are reducing the error. Okay, so this is what we are going to do it now. So how actually it's the equations that we are going to deal with if we are having multiple traps rule. We have two ways to calculate. Maybe you want to make it into this form, use this equation here, or you use just only one equation like this. Okay, so it's up to you, the decision back to you. If we are talking about the original equation, so the integral will be equal to h, which is, as previously remember, it's the integral is equal to b minus a times the function of a and the function of b over 2, right? So it's the same here. H is this area here, and the function of 0 plus the function of a is exactly this part over 2. Then you go for the second segments. So let's talk about these segments in here. From A to B, this is h. From here to here, this is h. And this is the function of x0 plus the function of x1 over 2 over 2. Then you go for the second segment. H, it's from x1 to x2. This is h. And the function of x1 plus the function of x2. So you are calculating here till you finish all the numbers of the segments. Or what you can do here is just only by using this equation in here, which is more easier because it's just only one shot. The integral will be equal to b minus a, the function of 0, so this means the first point here, the function of 0, plus 2 times the summation of all the function in the middles. So in our case in here, let's say that we are from x0, our limit from x0 to x3. So my internal points here is the function of x1, this one, and the function of x2. So this is what I'm going to put into this part. 2 times the summation of the internal points, plus the function of n, which is the last function, is for x3. Right here, over 2 times n. N, it's the number of the segments. N, it's the number of the segments. How many segments I have here? 1, 2, and 3. So 2 times 3. Okay. So let's see this one in the same example that we have done. And by the way, it's to calculate the error for the multiple application of traps. We are using this type of equation. Okay, so this is how we are going to calculate the approximate error for the multiple application of traps rule. Okay, so let's see the example. This is the function is given. Our limits, it's from a is equal to 0 to b is equal to 0.8. We already have done part A. So now let's make it for part B. But here they are asking us is multiple applications on traps rule using 2 segments. Okay, and this is the internal values. This given is the true values to calculate the analytical or to calculate the relative error. Find the true percentage relative error and estimate the error of the traps rule. So to make this one with the 2 segments, okay, this is the way. Our limits is from 0 to 0.8. So from 0 to 0.4, this is considered is my first segment. And from 0.4 to 0.8, this is considered my second segment. Okay, so if you are going to calculate based on this equation here, based on this equation, so this means you are going to take just only from here to here. You are going to take these 2 parts only. But we are going to use this equation here. So the integral will be equal to b minus a. So this means from 0.8 minus 0 times the function of x0, which is 0.2, plus 2 times the internal points, 2 times 2.456, plus the function of xn, which is the last value here, so it's 0.232 over 2 times 2, because how many segments I have here is 2 segments, from 0 to 0.4 and from 0.4 to 0.8. So it's 2 segments. So it's 2 times 4. So I'm going to calculate, I will get the answer of 1.0688. Okay, I want you to try this. This is the answer here on the textbook. This is example 21.2. This is how is the arranging of the numbers. But I want you to try by yourself. If you look at the textbook, the example is there. It looks really easy, but I want you to try it by your hand. Okay, to try to fit all this data into this equation here. Okay, so e minus a, 0.8 minus 0 times first value of the function of 0, it's 0.2 plus 2 times the internal points, 2.456, plus the last point, which is 0.232 over 2 times n. How many segments I have? 2 segments, from 0 to 0.4, and from 0.4 to 0.8, 2 segments. You're supposed to get the answer of 1.0688. Try to find it. Okay. So once you're done, since we are having the value, the true value, so that means you can simply calculate the error. The true value minus the result you get, so it's 0.57. Okay, now I want you to compare. Previously, when we are doing single application of traps, our error is 89.4. When I add one more segment to traps, the error now reduced to be 34. So this means the more you add segments, the more you are going to reduce the error. But what I want you now to do, because calculating the relative error, it's really easy. I want you to calculate the approximate error using this equation here. You need to find the mean of the second derivative of the function, which is, you already have done it. So it's equal to negative 60. You need to get the error, it's equal to 0.64 using this. It's b minus a, 0.8 minus 0 cubed over 12 times the number of the segments. So 12 times 2 squared times negative 60. You're supposed to get the answer of 0.64. Try to get that answer. And when you are going to see it, that this value here, it's more or less than 2.56. Single apps is 2.56. Two single traps, 2 segments of traps, it will give you the answer of 0.64. Try it. Okay, so now that's the idea that we want to deliver here. It's when you are going to do your calculations for the integral, if you are going to just only use one segment, the error is going to be really huge. If you add more segments, it's going to be better for your calculations. Okay, so this is what we are going to try to do it from starting now and so forth. Okay, so now is the last method for today is the Simpson rules. We are going to have here is more accurate of estimates. Remember, is my first slide here, we are talking about the integrations that we are saying. If you are going to use a first order polynomial, which is the Trapezoidal rule, they are going to give you a straight line. The straight line, the error is going to be really huge. But if you are going to use a parabola, which is going to give you a curve, the curve is going to be more accurate than you are using a first order polynomial. Okay, so let's see how this one. The parabola actually it's representing the Trapezoidal Simpson rule. So the Simpson rules, it's more accurate estimates of an integral. It's obtained if the higher order polynomial is going to be used to connect the points. So of course, it's going to give you a curve. So we are having two types of Simpson rule. The first one, we call it's Simpson rule 1/3. And the second one is Simpson rule, it's 3/8. Okay, what's the difference between them? It's really easy. The difference between them, that it's 1/3 rule here, it's connecting a parabola with the 3 points, 1, 2, and 3. Or what we call here, it's x0, x1, and x2. Okay, 3/8, it's making the area under the curve connected with the cubic equations for 4 points. Okay, so you're having 4 values of function, 1, 2, 3, and 4. Or what we call it is x0, and this one is x1, x2, and x3. So when we are looking also for that, if I'm having from 1/3, how many segments I have? From x0 to x1, this is your first segment. From x1 to x2 this is your second segment. If we are talking about 3/8, how many segments I have? This is your first segment, this is your second segment, and this is your third segment. So the difference between 1/3, it's 1/3, it needs 3 points and 2 segments. 3/8, it needs 4 points. These 4 points will create for you 3 segments. This is the difference between them. And you need to remember that because you are going to use them when you are going to solve any questions coming from the Simpson rule. Okay, clear? Any question about how to differentiate between 1/3 and 3/8? Okay. So let's start with the Simpson 1/3. So we are saying that it's Simpson over 3. It's using 3 points. So when you are saying about 3 points, of course, in your mind, your limits is going to be x0, x1, and x2. So you are having those 3 x's value. So the equation for the Simpson rule to solve for the integral, it's this equation here. So the integral is equal to b minus a, the function of x0, the first point, plus 4 times the function of x1, the middle point, plus the function of x2, this is the last point, over 6. The only things in here is x1 is not going to be given. When you are going to have a question, the question is going to tell you that it's a is equal to, let's say, 0, and b is equal to 0.8, which is a here is equal to x0, and b here is equal to x2. So what's the value of x1, which is for this one? The value of x1, it's the middle way points between a and b, or between x0 and x2. So where a is x0 and b is equal to x2, and x1, it's the midway points between them. So how to get the value of x1? It's b plus a over 2. So you will get the answer of x1. Okay, but now look how we are going to calculate the error of the, and by the way, this is not ET, this is EA, is the approximate error. How to calculate the approximate error of the Simpson rule? You need to get negative p minus a power 5 over 2880, and here it's f, the mean of the fourth derivative of the function. The mean of the fourth derivative of the function. The 4 in here, instead of we are making 1, 2, 3, and 4, which is going to be difficult to read. That's why they are making here number 4. You need to, and the z sign here, that's mean you need to find the mean. Or we can just simply write it like this. You just make a dash line. This means you need to find the mean of the fourth derivative of the function. Okay, so let's see how we are going to do that, because our first example here is asking, if I'm going to have this function, I need to use the following method to estimate the integral is given between a is equal to 0 and b is equal to 0.8. So it means x0 is equal to 0 and x2 is equal to 0.8. The first one using a single application of Simpson 1/3. Okay, so now single application of Simpson 1/3. How many points? 3 points. Okay, so let's do that. So since we are saying here it's the midpoints between 0 to 0.8 is going to be equal to 0.4, right? So it means from 0 to 0.4, I have 3 points, 0, 0.4, 0.3. These 3 points will create for me 2 segments. My first segment from 0 to 0.4, my second segment, it's from 0.4 to 0.8. Okay, so now I'm going to use this equation here to find the integral here. So b minus a, 0.8 minus 0, the function of x0, which is 0.2, plus 4 times 2.456, plus the function of x2, which is 0.232 over 6. I'm supposed to get the answer of 1.36747. Try it. And I think this example in your textbook is 21.4. This is the example in the textbook. You'll get the answer of 1.36. Okay, of course, we already have the true value. So the true value minus this results, you get the answer. So no problem with that. But now, if you're going to compare the relative value here, you can look from here. It's single ellipse or single segment of Simpson 1 over 3 is giving you the answer of 16.6% relative error. We have done this one with the 2 segments of traps. Still, the error is considered high. It's 35. So this means single segments of 1 over 3 Simpson rule. It's more accurate than maybe 1 segment or 2 segment or 3 segments using traps. That's why it's more accurate. Okay, so now I want you to try this equation in here to get the answer of the approximate error, which is 0.24. Remember that this one here, it's the mean of the fourth derivative of the function. I'm going to give you about 5 minutes to get the answer. It's supposed to be this portion in here, or the mean of the fourth derivative of the function is equal to negative 2,400. You need to get this answer here for this part. The mean fourth derivative of the function. So you need to differentiate 4 times. And again, you need to put it inside this equation here. To find the mean for this part. I'll give you about 5 minutes. Okay. Okay, you get the value 0.27. Okay, so that was the answer for the single segments of Simpson 1/3 rules. So in the same pattern, if multiple application of Simpson 1/3 rule, it will improve the accuracy of the application of it. So how we are going to do that? So we can improve by dividing the integration interval between the limits into a number of segments. But here we need to be careful here, because the number of the segments that we are going to include, or we are going to add to 1/3, it's based on a conditions in here. So it's limited to the case where we are going to add these segments supposed to be in values of equal space. So this means the step size must be exactly the same. So between x0 to x1 supposed to be equal from x1 to x2, and from x2 to x3 is supposed to be, they are equal to each other. The step size supposed to be equal, must be equal. If you see the value of the step size is different, so you cannot use the multiple application of 1/3 rules. And another thing is that you are limited to, you need to be limited to the where it's going to be even number of segments and odd number of points. For 1/3, when you are going to make a multiple application or multiple segments, you are limited to where it's going to be even number of segments and odd number of points. That's why I told you here from the beginning, you need to remember this. It's 1/3. It needs 3 points, which is considered odd, and even number of segments, because 1, 2 is an even number of segments. 3/8, it needs even number of points and odd number of segments. Okay, so this is the limitation of 1/3 multiple segments. So the step size must be exactly the same, and they are limited where you can make even number of segments and odd number of points. So what's the equation will help us to calculate the multiple application of 1/3? This is the equation here. So the integral will be equal from b minus a, the first point of the function, which is coming here, x0, plus 4 times the summation of the points with 1, 3, and 5, the odd points, plus 2 times the summations of the function they are having even points, plus the last point, over 3 and n is the number of the segments. And this is how to calculate the approximate error. Okay, you need to find the mean of the fourth derivative of the function. Okay, so the most tricky one in here now, it's this part, how you are going to find the odd points and even points. So let's see it how from the example. The example is asking to use the multiple application of Simpson 1/3 rules with n it's equal to 4. So you can see from here n it's equal to 4. Remember that we are saying that here we need to get the even number of segments. So 4 is considered is an even number, and this 4 is going to give us 5 points. So this means x0, x1, x2, and x3, and x4. So these 5 points will give us 4 segments. So now let's see how we are going to solve this. So this is the equation. Okay, I put the index here. This is to show to you the 1, 3, and 4, 1, 3, and 5, 2, 4, and 6. So those numbers, you are not using them inside your calculations. Those numbers is just only to show you the even and odd points. Okay, so we start from 0, and this is the last point. Okay, so b minus a, so this means 0.8 minus 0. The function of 0, so it's 0.2 plus 4 times, so this is 4 is going to be times this value and the 3 1. Can I take this one? No, because this is for 4, right? So 1, 3, and 5. Is it clear what I mean here about this part? Any question? It based on the number of the segments. Remember here, it's asking for 4 segments. So how many segments they have in here? From 0 to 0.5, from 0 to 0.2, this is your first segment. This is the second segment. This is the fourth segment. Okay. We are asking here for 4 segments. So this is giving us the segments. 1, 2, 3, and 4. So the index, if asking for another segments, this index will be increased. Clear? Okay. So now you know why I am highlighting this one is because this is 1, 3, and 5. So I cannot take 4 here. Okay. We finish with this part. So now plus 2 times the even points, which is 2, 4, and 6. So it's going to be 2 times, we say this value. Can I take 4? No, because this is the last value which is going to be here. So be careful. You cannot take 4 because this value here is considered is the last value. So this value here is your last. So you cannot use them. And this one you cannot also use it. So this value is here, fx0, and this value here is fxn. So I cannot use it here. 1, 3, and 5. You can use this and this. And 2 times the summation of 2, 4. So this is the value, but I cannot add this one in here. Over 3 times the number of the segments. 3 times 4. So it's supposed to get the answer of 1.623. Okay. Anybody have any questions about this color and what does it mean, or how to get these 2 items in here inside this equation? Any question? Clear? Okay. So when you are going to done your calculation, you are going to get the answer of 1.62347. Try. And also try to calculate the approximate error, which is 0.017. Who's doing it since morning? Is it Muhammad? Who's the one replying me from the morning? Who's the one saying grades here? Oh, it's you. Okay. Seems like you're the only one here. The rest, they don't care. Okay. So that was for the 1/3 rule. So now is the last thing here. It's the Simpson 3/8 rule. So remember, is single application of Simpson 3/8. It needs 4 points, and these 4 points will create for you 3 segments. So an odd segments and even points are used to conjunction with 1/3 to permit evaluation for both even and odd numbers of the segments. So since we are talking here about the 4 points, so you are going to have x0, x1, and x2 and x3. And of course, if you are having the limits from A to B, so I know that it's all the Simpson rules, they are working with the same step size. So equispace. So this is how to get the step size based on the number of the segments. So for our case in here, h will be equal, for our example, it's from 0.8 minus 0 over the number of the segments, so over 3, because the single application of 3.8, it will get about 3 segments. So you can get your step size, to get the step size. Okay, this is the equation that is going to be help us to calculate the integral b minus a, the function of x0 plus 3 times the function of x1 plus 3 times the function of x2 plus the function of x3 over a. And this is the equation how to calculate the approximate error. Okay, you need to find the mean of the fourth derivative of the function, and you need to divide over 6,480. Okay, so now this is the example. The example is 2 parts. So now we are going to solve part A, which is solve for this function from the limits a to b using one application of 3/8. So the first things we need to do in here, we need to find the step size. Okay, so to find the step size, h, as we show here, b minus a over n. So it's 0.8 minus 0 over the number of the segment. So you will get the, so this is 3. So you will get the step size. So my step size here is 0.26. Okay, so of course my first point is 0. So this is x0. x1 will be equal to 0.26, and x1 will be equal to 0.53, and last point is equal to 0.8. Do you know how these things came up? Based on the step size. My first value is 0 plus 0.26 plus 0.26, so it's 0.53. 0.26 is going to be 0.8. Is it clear how to get those values? x1, x0, x1, x2, and x3. Clear? Okay, so these values you are going to put it inside the original function, which is this one. So when x is equal to 0, so you get the answer of 0.2. When x is equal to 0.26, so the function, this function here will be equal to 1.4, and so on. So you get all the values of the function now. Okay. So you will just put all these values here. b minus a, 0.8 minus 0, 0.2, plus 3 times 1.4, plus 3 times 3.4, 0.232 over 8. So the answer is 1.519. Try it. Try to get this answer. Okay, so that's good. Okay, the last part here. Simpson rule 3/8, it doesn't have multiple application, doesn't have multiple segments, but it can work with the conjunction of 1/3. So that means if you want to enhance the accuracy of Simpson 3/8, you need to combine it with the 1/3. So now before we start to explain, if I'm going to combine 3/8 rule and I'm going to combine it with over 3, how many points I'm going to get and how many segments I'm going to have? I want to combine 1/3 rule with 3/8 rule. So how many segments I'm going to have at the end? And this segments is created by how many points? Five segments, correct. So this five, how many points? Six points, right? Okay, so this is the way how we can make the conjunction of 1/3 over with the 3/8. Since 3/8 rule, it doesn't have multiple applications. So what we need to do, we are going to combine it with 1/3. So remember, it's 1/3 rules, single application. It needs 3 points to create 2 segments. And 3/8, it needs 4 points to create 3 segments. So the total up is 5 segments. 5 segments. As you can see it from here, 1, 2, 3, 4, and 5. This is the 5 segments. So how many points I have? 1, 2, 3, 4, 5, and 6. Okay, so that's mean the limit of my points in here, the step size here is 0.2, So from here to here to here, this is what I'm going to make it for 1 over 3 rules. So I'm going to solve from 0 to 0.4 or 1 over 3. So I'm going to calculate the first integral. So the limit from a, it's equal to 0, and b is equal to 0.4. This is for the 1 over 3. Then we will go for the 3 over 8. So 3 over 8, starting from 0.4 to 0.8. So this is going to create for me the second integral second. But the limit here is not from 0. The limit is from 0.4 to 0.8. So a is equal to 0.4 and b is equal to 0.8. Why we are making two integral? Because the equation to solve for 1 over 3 is not the same equation we solve for 3 over 8. So we need to have two integral, then we combine them together. So at the end, the total integral will be equal to integral first plus the integral second. Okay, so this is the idea, how we are going to make it. So when we are looking now at the example, use the Simpson 3 over 8 rule in conjunction with Simpson 1 over 3 rules to integrate the same function for 5 segments. So how we are going to do it? So of course I need to get 5 segments, right? So n is equal to 5 segments. So with the 5 segments, my step size is going to be 0.16. So my step size is 0.16. So 0, 0.16, 0.32, 0.48, 0.64, and 0.8. Okay. So now, the first 3 segments, I will take it for 1 over 3. So I want to take the first segments for 1 over 3. So this one, 1, 2, and 3. I will make these 3 segments. I am going to use them for 1 over 3 rules. So use the equation to calculate. The first integral using this equation. So what the answer you're going to get? Perfect. So you are getting this exact answer here. Okay. So now your next integral is to calculate for 3 over 8 because we are saying in conjunction with 3 over 8. So 3 over 8, it needs 4 points. These 4 points will create for you 3 segments. So you cannot start from here. If you start from here, it's going to be 1, 2, and 3. So you start from here, from 0.3. This is your A. So from here and here, now this is going to be 3 over 8. And this is the values. So this cells in here is sharing. So it's b for first integral and it's a for the second integral. So this is your a, this is your b. Now you are using this equation here to calculate for the second integral. All these things you are going also to find it here in the textbook. Perfect. So you are getting this value. So at the end, this mean is the area under the curve. So the area under the curve for this will be equal to this rule plus this rule. So you already have the values. So it's going to be 0.38 plus 1.26. So you're supposed to get this answer here as your final answer for the area under the curve, 1.64. Okay. So if you are looking now at this value here and looking at the true value, they are somehow near to each other. That's why it's the error, it's really reduced. So this value and this value, it's near to the true value. So the error is equal to 0.2. Okay. So I need to combine these two values together to get the total up. Okay. So that's all for all the Newton schemes for calculating the integration. Do you have any questions about? Any questions about any rules? Traps, Simpson 1/3, 3/8, or how to make a multiple segments of any apps? Any question?
No, sir.
Okay, so now what you had here is we already know about all the Newton codes scheme formula, so the traps and for the Simpson rule. But actually, you are not going to get the question coming from this part or the question is coming from this part. Means that you are not going to get a question in the final or in the assignment is asking you to use a traps rule or the Simpson rule by itself. Mostly the question is coming from this part, which is I'm going to cover it in the next class. The questions in the final or in the test mostly coming from this part. Integration with unequal segments using all these methods, which is we are going to explain it on the next class. So the question actually is coming from here. The integration with unequal segments. So a question will ask you to combine all the methods that you had learned, which is the 1/3, 3/8, and traps to calculate the integration for unequal segments. So this means the step size is not exactly the same. So next class, which is coming to in your lab session, I am going to teach you how to do that. And this is where you are going to start to have the questions coming up. But our class today, it's really important because you need to know how those methods works. How is the traps, how 1/3 rule, and how is over 3/8 rules it works, which is this one is going to be help you to solve. And after that, I'm going to start with the numerical differentiation, which is it's not something new, something you already explained on week 2, I think. So, but we are going to talk about the higher accuracy of it. Okay. So before I finish here, I want to clear up something here because I don't want you to repeat the same mistakes that we have done on assignment 2. I know that I am using Microsoft Excel to explain the methods, but why I am using Microsoft Excel to put those values like this and here in front of you to show you an example? Because I don't have the whiteboard, so to write by using my hand in front of you. So that's why I am using Excel. I don't have a whiteboard. So most of you making a mistake last time during the assignment when I'm asking for question number 3 using the MATLAB and using Excel. Especially for this type of question, because the question is asking you to solve for linear algebraic equation, right? So how many methods that will help you to solve for the linear algebraic equations we had learned? How many methods to solve linear algebraic equation? We are having Kramer rules. We are having Navier-Gauss, Gauss-Jordan, and Gauss-Seidel, right? And like, for example, in here, this is considered is Navier-Gauss. This one here is Kramer rules. This one in here is Gauss-Jordan. And I have also my Excel file to solve for the Gauss-Seidel, right? So when the question is coming to asking you to solve this one using Excel, it doesn't mean that you need to do this one. This is my explanation to you to tell you how is the method is working. Linear algebraic equation to be solved using Excel, you no need for you to write this Excel file. It's just only what you need to do. You just only having these equations in here. Okay, I'm going to show it to you. I already solved this one with you in the lab. I'm going to have this question. There is no here, it's Kramer rules. There is no Navier-Gauss, there is no Gauss-Seidel, there is no Gauss-Jordan. The only things to solve this one using Microsoft Excel is just only you need to highlight 3 cells. You are going to write it's equal to M inverse, highlight the cells, Control Shift and Enter. And here it's equal to MMULT, matrix multiplication. Highlight the first matrix, comma, highlight the second matrix, and Control Shift and Enter. But suddenly I find people, they are writing for me because the question is asking to solve using Navier-Gauss, Jordan, I think, and Seidel. They are writing the same exact Excel file I'm giving. Why you want to do that? I want to see that you understand how Excel can solve. Excel can solve linear algebraic equation just only by 2 functions, which is matrix inverse and matrix multiplication. The same also goes with the MATLAB. I never teach you how to do Gauss-Seidel using MATLAB. I just only using, I told you that it's in Excel, in MATLAB, you need to write using the MATLAB, you are going to write, I call it inverse matrix A times matrix B. That's all. But still, I find people, they are wasting their time going online to find how is the code of Gauss-Seidel and how is the code for this one. We don't want to show that. We already give you here in the lab. This is what I want to see. You know what's the command I give to you. So don't try to go beyond. Okay. So I hope that for the next assignment, if the questions is prepared by other lecturers is asking you to use MATLAB, to use Excel, don't try to go out. Is what I'm giving you inside the lab is this is what you want to use. But don't follow my Excel file for explanation. I am showing you here in detail just only to make things clear for you, but it doesn't mean that's mean if your next question is coming from the numerical differential integration, I don't want to see something like this. I don't want you to do this. Suddenly I find my Excel file is in front of me like that. You cannot do that because there is a specific command. You go for the data, you go for the solver, you go for this one. This is the way to solve. What I'm showing you here in Excel is I'm showing you the method, how it works. But sorry, I don't have a whiteboard behind me to explain it to you. Okay, that's why I'm using Excel, just only to put the numbers is fast. But at the end, you need to do it into this part. I don't want to show you the values like this. Okay, so is it clear now how it works?
Yes,
Okay, so our next lab session, if we finish fast, I'm going to solve with you the midterm exam, just only going fast how to solve, because some of you getting the values is like they never attend any classes with me. Even for the first question, they cannot answer it. So I will explain how to solve that. But I hope that you are going to recover that one during assignment 2 and also for the final. If you have any questions, please do ask. But before you leave, just only the attendance, because here you are group C and E. Please don't forget to write the name of your group. So your name, your student ID, and your group. If you have any questions, please do ask. If not, thank you very much. Have a nice day. I'll see you, inshallah, in the lab session.